The difference between a molecule and a compound is actually pretty simple. I'm going to put two examples up here. So for example, we'll do NH3 and we'll do O2, the oxygen we breathe. So this NH3, the name of that is ammonia. And then O2 is what we would say is just called oxygen. This is the oxygen we breathe, but more specifically it's oxygen gas. Now the difference between a compound and a molecule is the difference between these two, which is ammonia is nitrogen and 3 hydrogens all bonded together, and the oxygen is just 2 oxygen molecules bonded together. Well, a compound is going to be like ammonia, and a molecule is like the oxygen, where the difference is a compound is just going to be 2 different elements bonded together, and a molecule is the same elements, but multiple of the same. So multiple of the same elements put together. And that's all it is for note card number 1. 2 parts to this note card. A chemical formula is simple enough. It's just like H2O. It's a symbolic representation of a compound. So if I have H2O, what it truly looks like is this molecule that's got that shape, or it looks like this with a big oxygen right in the center. But a chemical formula is just the symbolic representation of that compound. Now, what do the subscripts mean? Well, if I rewrite H2O, the subscripts tell me how much I have of each individual element. And what it tells me specifically is how much do I have of the element that it comes directly behind. So in H2O, or in water, there's 2 hydrogen molecules. Now the question is, how many oxygen molecules are there? Well, it's going to be whatever number comes after oxygen, and if there is no number, we just assume it's just the number 1. So in water, a subscript is 2 hydrogens and 1 oxygen. Atoms bond and form compounds for one very simple reason, and that is what we say is to become happy. So how do they actually become happy? Well, it's based on their valence electrons. The answer is they want to become stable, and how they become stable is to be similar to noble gases. So if we remember from our last chapter, noble gases have an electron configuration, but more importantly, the electron configuration, let's say of neon, is going to be 1s2, 2s2, 2p6. Well, that says that in its outer shell, or if I did the Bohr model for it, looks like this, its outer shell is going to be full. Most of the time that means that there's 8 valence electrons, but that really just means they're stable when their outer shell is going to be full. So atoms bond and form compounds so that they can get an outer shell that's full. So the outer shell must be full. For everyone that's 8 valence electrons, except for hydrogen. Hydrogen just wants 2 valence electrons, and we'll get into how they get those valence electrons. The octet rule is very simple. Octet means 8. So the octet rule is that for any atom to become stable, they are going to have to reach 8 valence electrons. Now, how they get 8 valence electrons is through chemical bonding, and there could be one of 2 options. One way could be like sodium chloride, where I have sodium, and we're just going to draw its outer shell. And we have chlorine. Well, chlorine has 7 valence electrons. So 7 of its outer shell is full. Sodium just has 1 valence electron. So what sodium and chlorine are going to do is sodium's going to want to get rid of its valence electron, and chlorine's going to want to take it, because when that is gone, when it's given over to the chlorine, sodium's new outer shell is the one that was just underneath, which is now full. So they're either going to be like sodium chloride, or they're going to be like water, which is H2O. And the difference is water, oxygen, has 6 valence electrons, and the hydrogens each have 1. Oh, excuse me, there should just be 1 here. And instead of getting rid of them, everyone's going to be happy if they start sharing them. So this hydrogen is going to share with this oxygen. This hydrogen is going to share with this oxygen. So anything in the circle is said to be owned by both of them. The octet would be 1, 2, 3, 4, 5, 6, 7, 8 for oxygen, and the hydrogen gets its 2 that it would like to have the outer shell. Now again, octet means 8, but it also means for hydrogen, it just wants 2, so maybe a better definition of this would be it wants its outer shell to be complete. An ionic compound is any sort of compound similar to sodium chloride. We're going to use that as our main example here. It's any compound that is between a metal and a non-metal. There are other definitions to it, which we'll get into with other note cards, but the main difference is that there's 1 metal and 1 non-metal. Now, how that works is our first one, we call that a cation, is an ion that's always the metal first, and then we have our second element like chlorine here, which is what we call an anion, which is going to be our nonmetal. Now, we see that though both of those two words have the similar root word of ion, so we have to now define what an ion is. Well, an ion would be like Na plus 1, or chlorine minus 1, minus 1. Oh my goodness, minus 1. An ion is any atom with a different number of protons and electrons. Or another way that we can say that is a charged atom. How they get these ions, well, they are naturally ions when they're all by themselves. If I just pluck an element from the periodic table, it's going to naturally be an ion because they're going to have a certain number of electrons in their outer shell, and they're going to want, in order to become stable, like we said previously, they're either going to want to lose an electron or they're going to want to gain one. So how ions form is when they gain or lose electrons. Our previous example was with sodium and chlorine. When we draw how many valence electrons each one has, chlorine, based on its group 17 on the periodic table, has 7 valence electrons, and sodium just has 1. They become ions when they gain or lose an electron. So naturally, sodium is going to want to get rid of its electron and give it to chlorine. So now chlorine has 17 protons, but now it has 18 electrons, so we think of it like adding in a negative number. 17 plus negative 18 gives me a negative 1. Sodium has 11 protons, and it now only has 10 electrons, so when I add those together, I'm going to end up with a positive 1. So ions form when an atom loses an electron or gains an electron in order to become more stable or to find a partner that's willing to take one or two or give one. What is the difference between polar and nonpolar bonds, and more importantly, what's a covalent bond? Well, covalent bonds are going to be broken into two types. They're either nonpolar or they're polar. And those nonpolar and polar compounds, what's similar between all of them is when they're covalently bonded, they are one of two things. They're either two nonmetals, so I'll just do two nonmetals bonded together, and those two nonmetals are going to share electrons between themselves so that everyone can reach that octet of 8. The difference between polar and nonpolar is whether or not they share them equally, so equally shared, or whether they share them unequally. So for example, for nonpolar compounds, ones that share pretty equally are going to be like chlorine and chlorine. Each chlorine has 7 valence electrons. I'm going to do them kind of opposite so we can see them here. And what chlorine wants to do is it wants to have 8 valence electrons. Each chlorine only needs 1, so what's going to happen is instead of this chlorine holding this atom or electron and this one's holding this one, they're now going to suddenly share both of them in the middle. And we say that both of these atoms have these 2 outer shell electrons, so that chlorine now has 1, 2, 3, 4, 5, 6, 7, 8. This one has 1, 2, 3, 4, 5, 6, 7, 8. Now, those are considered nonpolar because they equally share them. Not one chlorine has more or less of the electrons its way. For polar, a great example of that was probably, well, we'll just do water. So water has hydrogens and oxygens. There's some lone pairs on the oxygen, but what happens is this oxygen is going to pull some of these electrons a little bit closer to itself than the hydrogens are going to. So these two are going to be shared between the two atoms. However, they're going to be mainly pulled towards the oxygen, so this oxygen has more of a negative charge towards it, and this molecule has more of a positive charge on this end because the electrons are more so towards that side, or they're being pulled more unequally by the oxygen. We call that having a dipole moment. These polar compounds are a big reason why water is the way that it is, and we'll get into more of that later, but essentially here all we need to see is what is the difference between covalent compounds, whether they're polar or nonpolar. They both share electrons, it's just whether they share them equally or unequally. The example I like to think of is like with a cookie. So if you have a chocolate chip cookie and you're sharing it with your friend, when you're going to share the cookie, you're going to have to split it, but let's say you split it like this. You'll probably take the bigger side if you get to choose, or your friend will if they get to choose first. This is more of an example of a polar covalent compound. You're both sharing the cookie, it's just one side has more than the other, whereas a nonpolar cookie would look more straight down the middle, where everyone gets the same size of the cookie, or everyone is sharing that cookie. There's 3 types of bondings that we're going to have to classify or differ between. The 2 main types are ionic and covalent. However, under covalent, we just learned that there's nonpolar and there's polar compounds. So we have to be able to determine, okay, what type of bonding is it based on the formula. So what we'll do is we'll get something like HF, or hydrofluoric acid. Well, I want to know, is it going to be ionic, polar, or nonpolar? So what we do is we have to make a little bit of a chart where we have ionics, we have polars, and we have nonpolar. What we're going to have to do is we're going to have to subtract the electronegativity of each of the atoms here. One's hydrogens, one's fluorines. Once we subtract the electronegativities, wherever they line up is going to determine, is it ionic, polar, or nonpolar? Because that tells me who's going to be pulling more than the other, or the term, or the property of electronegativity. So if I subtract their two electronegativities and I get a number that's greater than 1.67, we would classify that as ionic. If I get it between 0.3 and 1.67, we classify that as polar, and then nonpolar is going to be 0 to 0.3. So again, sharing equally, ionics share very unequally. So let's go ahead and do it. Well, if I find hydrogen and I find fluorine on the periodic table and I find their electronegativities, when I subtract them, I would find that there's an electronegativity difference of 1.9. So you tell me, would that be ionic, polar, or nonpolar? Well, that's going to be ionic. Now, you might be asking yourself, why is that ionic if it's two nonmetals put together? Well, there's going to be a type of compound we learn next chapter. We're going to learn all about the acids, and this is considered an acid, which have very strong difference in electronegativity. That hydrogen is going to release very quickly, but for now, all we need is to make sure we have this chart in for our notes. I have the rules listed here for how the electron dot structures are written for atoms. So these are the 3 steps that we would use. I'm going to go ahead and do one really quickly for you. So let's do magnesium. You're going to be given an element, and you have to draw the electron dot structure for it. First is we write the symbol for the element, check. Second is we use dots to represent the valence electrons. So if I find magnesium, it's in group 2, it's an alkali metal. So it's going to have 2 valence electrons. So we use those dots, 2 dots, to represent valence electrons. And third, arrange the electrons around the symbol one at a time until all the electrons are in place. Well, it's going to be based on this square. Imagine it's the square on the periodic table. Each side is very similar to Hund's rule, where each side of these is like a bus seat, and only one person can sit on the bus seat until all of them are filled. So we have 2 valence electrons to do, so we'll fill up one side and fill in the other, and this is it. Well, I don't really like using the box all that often. Let's go ahead and do something like sulfur. Sulfur is in group 16, so it has 6 valence electrons to use. So I'm going to fill up each side until there's one person in each seat. I've used 4, so I have 2 more remaining, and I just keep going clockwise. So it's going to look like 6 dots all on the outside for sulfur and 2 for magnesium, following the 3. So when writing Lewis structures, our whole goal by the end of it is to create a compound. And we want to know exactly how many bonds there are, what are the types of bonds, are they single, double, or triple, and then it's going to also be able to tell us the shape eventually when we get into VSEPR theory. So for right now, what we have to do is we have to be given a compound. The first compound we're going to try and do 2 examples here. The first one we're going to do, let's start with CH4. So that's 1 carbon and 4 hydrogens. What we have to do first is identify the type and number of atoms in each molecule. So I have carbon and I have hydrogen. Step 2 is I need to count the total number of valence electrons. Well, carbon is in group 14, so it's going to have 4 valence electrons. And there's only 1 carbon in the whole formula, so I would take 4 times 1 to see how many total valence electrons I get to use, or dots to draw, and that's going to be a total of 4 valence electrons. Hydrogen has 1 valence electron, but there's 4 hydrogens in our formula, so that's going to be another 4 valence electrons, and my total is now going to be 8 valence electrons in total. Step 3 is draw a skeleton structure for each molecule. My skeleton structures are supposed to be dependent on, similar to our last one, if I had magnesium, we have a square, we can fit 4 elements, 1 on each side of the square. If carbon is present, I'm going to put carbon in the middle, so that means I'm going to arrange all of the other atoms around the central atom. Kind of make its own little box, 1 on each side. If I don't have carbon, then I'm going to use the one that I either have the least number of, in this case I only have 1 carbon, so that would stay in the middle, or find the one that has the smallest electronegativity and do the same. So that step is done. Step number 4, connect each atom with a pair of electrons. That is going to be equal to 1 bond, and I can do that with either dots or minus signs, and then put electrons around each atom until they all have 8, except for hydrogen. Hydrogen just wants 2 valence electrons. So I'm going to do that. I'm going to place dots between every atom. And again, if there's dots between the symbols, between the 2 letters, that means both sides are going to have that many valence electrons to hold. In this case, this carbon is going to have 8, because I put electrons all the way around it, 2, 4, 6, 8. And each hydrogen is going to only have 2. Step number 6 is count the total valence electrons used. If they equal the original number of valence electrons, I'm done, which this is the case here. 8 dots around here, 8 valence electrons used total. This one is done. This is what its final shape is going to be. However, what I'm going to show you next is going to be multiple bonds, whether double or single. All I'm going to show you right now is the final version of that, which is going to look like this, where N2 is going to have a triple bond between them, and each one is going to have 2 extra dots on the outside. We'll get more into that with note card number 10. However, this total number of valence electrons here, the lines, again, are the same thing as 2 dots put together, 1 bond. This one's going to have what we call a triple bond in it, which is where we share 3 pairs of electrons. So this nitrogen here technically does have 8. This one also does have 8. We'll get into why here in a second. A multiple bond is where 2 atoms are going to share more than just 2 valence electrons, or they're going to share more than 1 pair of electrons. How that happens is like in our last step here. When we look, if I used too many dots to make everyone happy, then I have to start sharing them up. Or it's really, I have to become more efficient. So I'm going to give you 2 examples here. We're going to do SiS2 and we're going to do HCN, or cyanic acid, hydrocyanic acid. The first one for SiS2, I'm going to have to take and count how many valence electrons I get. Well, silicon is going to give me each 4 valence electrons. There's just 1, so that's 4 valence electrons total. Each sulfur is going to give me 6 valence electrons, and I have 2 of them, which is a total of 12 valence electrons, so my total number I get to use is 16. Well, we're going to start seeing that certain numbers represent certain bonds, certain number of valence electrons to use. But for this, I'm going to walk through it. What we have to do is we have to make everyone happy first. So I'm going to put 8 dots around everyone. Again, if they're in between, they're going to be shared. However, the issue here is if I count out how many dots I used, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I've used 20 valence electrons, and I can only use 16 of them. So what I'm now going to have to do is I'm going to have to start erasing some dots, or some electrons. In fact, I have to get rid of 4 of them, and then I have to make everyone happy and rearrange after that. So what I'll do is I always like to do symmetrically. I like to take off 2 from each side to get rid of 4, or take off 1 set of 2 on one side and 1 set on the other. Now I have 16 dots. However, when I draw it this way, I have 2, 4, 6, 8 on this silicon, but each sulfur just has 6. So what we'll have to do is we're going to have to start moving some around. Now silicon in the center is going to be, for us, creating a covalent bond, which means it's going to keep all the electrons, but it's okay with sharing them with someone else. So as long as the silicon keeps its 8, it'll be happy. So once we get down to the number we want, I now have 16 valence electrons, the silicon is going to take some of it that are what we call a lone pair, and it's going to start sharing them with the other atoms, sharing them to make everyone happy. So these 2 and these 2 are going to start moving off. So how I would rewrite that now is those valence electrons, well, those will be okay right there. Those valence electrons are now shared between the atoms. This sulfur has 2, 4, 6, 8, because those 4 are between them, they share both. The silicon has 2, 4, 6, 8, and this sulfur has 2, 4, 6, 8. Everyone's happy. There's a total number of 16 valence electrons. I can redraw it like this if we want, but now everyone is happy. What we call these right here are double bonds, or 2 pairs of the valence electrons being shared. Now when I go up to hydrocyanic acid, we're going to see that it's going to be a little bit more difficult than that. 1 valence electron from the hydrogen, 4 from the carbon, and 5 from the nitrogen. Gives me a total of 10 valence electrons to use. Carbon's going to go in the center, hydrogen and nitrogen will go on the outside, and when I go ahead and make everyone happy here, we're going to find that I used way too many. In this case, I've used 2, 4, 6, 8, 10, 12, 14, and I can only use 10 here. So what I'm going to have to do is I'm going to have to erase some, and I'm just going to go ahead and erase from the outside. I want to keep this hydrogen happy because it only has 2 to use, but now this nitrogen just has 2, 4 of them. This carbon is going to be a good friend. It's a covalent compound, so they're going to share. So it's going to take whatever lone pairs it has, and it's going to start sharing them with the nitrogen so that everyone can be happy. So this hydrogen is going to keep its 2. The carbon keeps its other 6. It's just now they're between the nitrogen and the carbon. This nitrogen just had one set of its own lone pair remaining, and now we're good to go, where we have 2, 4, 6, 8 on this carbon, 2, 4, 6, 8 on this nitrogen, and the only 2 that hydrogen needs right here. So this is what we call these 3 together. We can call that a triple bond, or we can redraw that as such. 1, 2, 3 lines with 1 line just for that. So we can have double or triple bonds. How they form is in order to get the total number of valence electrons we can use to match the total number of valence electrons in our Lewis structure. One thing that might get a little frustrating with these Lewis structures as we get better is we're going to start finding something called exceptions to the octet, where that just means everyone wants 8, but sometimes they don't get them just to get happy or just to get included. So, and a great example of that is BH3, or boron trihydride, where we have boron in the center, we have 3 hydrogens on the outside. This boron is going to give me 3 valence electrons, and each hydrogen is going to give me 1, but since there's 3 total, I'd have a total of 6 valence electrons. Well, the only possible way for this to work is if these 3 hydrogens are happy with 6, and this boron is just okay with only having 6 of them. Well, that's going to be okay. Sometimes I might reference this thing called an exception to the octet, where if I give you a compound and say, give me the Lewis structure, this is an exception to the octet, that means everyone's going to be happy on the outside, but the central atom is going to be the only unhappy one here. So this is actually what the structure is going to look like, where it'll look like 3 single bonds between this boron, and that's it. It only has 6 valence electrons. Or another example we could get that's a little wild is XEF. Let's do XEF6. Let's see how that goes. So we have xenon here. Oh no, XEF4, sorry, excuse me. So there's 4 fluorines, but each fluorine here is going to give me 7 valence electrons. So 7 valence electrons times 4 is 28 from the fluorine. And then I get another 8 from the xenon, because it's a noble gas there. So I'm going to have a total of 36 dots to use. Well, if I make everyone happy, I'm going to end up with 8 on each of these fluorines. And this xenon is going to have an additional 4 somewhere. I've only used 32 dots so far, but I have 4 more to use. Well, this xenon is just going to get 2 extra dots on each side of it. So the xenon, instead of having 8 total, it's okay with having 12. We'd call that an expanded octet. This boron right here is okay with only having 6. As long as the outer arms are okay, then everything is okay. The last part of this is something called the resonance structure, which just means there's multiple ways to draw the same structure. I'm going to go ahead and give you an example for ozone, where ozone has 3 oxygen molecules. It's going to end up having a double bond, where this oxygen here is a lone pair, this one has 2 lone pairs, and this one has 3 on the outside. Well, a resonance structure could be, I could draw the same thing, where I have 3 oxygens. It's just the double bond is on this leftmost atom instead of on the right, like this one example here. Or I could even go wild and make a wildly different shape, where everyone here gets a double bond. Where everyone here could get a double bond, and we would have enough. Well, that's what we call a resonance structure, where there's multiple ways to make the same compound. Usually it's represented with an arrow between them. Sometimes I might ask for you to give me all of the resonance structures for a certain compound, but a resonance structure just means different ways to draw the same compound. An exception to the octet says that while the center atom might not get 8, everyone else will be, and they will be happy. So this compound is how it would form in the natural world. Before we get into our last bit of this chapter, where we start exploring polyatomic ions, things that are going to be breaking the rules that we've been talking about thus far, I want to first compare ionic and covalent molecules one final time. Well, one big difference between the two for us is, in order to identify them, it's going to be a metal plus a nonmetal for ionic compounds, and we're going to have a nonmetal and another nonmetal to make covalent compounds. The example here being H2O for water, or we get, let's say, magnesium chloride over here, where metal and a nonmetal are cation and anion, whereas we just have 2 nonmetals there for that covalent compound. Other options that we might have are going to be other specifics. For example, ionics dissolve in water, whereas covalents don't dissolve in water, or if they do, they don't totally deionize. They just start separating out, or not deionize, they don't ionize. These are going to have a high melting point or boiling point. These are going to have a low melting point or boiling point. But more importantly, a way that we can think of this is conductors or not conductors. Or insulators would be another word for it. But really what it boils down to is most of these these properties come from the idea that ionics hold on to each other very, very well. One element really wants the electrons, so it's going to hold on to them. The other one does not want them very much, or they're just going to share them between them. So because of that, we're going to get very high melting points because they want to hold on together. However, they're going to be great conductors and they dissolved in water because water is polar, where there is a more negative side and a more positive side. Well, because these are all only bonding together because of their charges, the more positive cation and the more negative anion are going to also be attracted to the polar and nonpolar sides of water. So covalent compounds aren't going to separate as much, but the ionics are, because they're going to separate into ions, which are good at releasing their electrons, giving us electricity, and really good at that when dissolving them. So polyatomic ions are going to be really important to us later on, especially in our next chapter, where we're going to be given things that are forming a bunch of different compounds, because polyatomic ions are really good at forming other compounds, but they're going to look really complex to you because they're going to be multiple atoms that are all bonded together. Well, what we call those are polyatomic ions, or more commonly, they're going to be polyatomic ions. It's going to be really important for us to know their names and their formulas for these 10 at the very least. Because our next chapter, we're going to see these a lot in different compounds. So polyatomic ions are seen rather often in the natural world because they're covalently bonded molecules that do have a charge themselves. Because they have a charge, they're going to form ionic bonds with other molecules or with other compounds. So they are covalently bonded themselves, but they're going to act like ions together because they don't have enough, or they might have too many valence electrons. So in this case, in this example, I have it drawn incorrectly, but I have nitrogen as having 5 valence electrons. This hydrogen, though there's 4 of them for ammonium, ammonium is NH4+. So I'm going to have a total of 9 valence electrons to use. Well, if I redraw these so they all match the same color, they only need 8. The hydrogens only need 2 valence electrons each. This nitrogen's already got its 8, so it has 1 more to get rid of. So how we draw that is we throw a box around it and we give it an overall positive charge. So this is going to have 1 more electron, think of it like floating off to the side here, that this ammonium is willing to give to someone else. If I were to do phosphate, PO4 3-, it's going to have a total of 5 valence electrons from that phosphorus, and we're going to have a total of 24 from that from all the oxygens. It's going to have an additional 3 because it has a charge of a -3, which is going to get us to our overall charge of 32. Well, if I did 32, we should know that that's going to make this kind of shape where everyone is going to have 8. There's no double bonds. It's all single bonds for everyone, and it's all happy. How we denote that is with a -3 on the outside of it. It is now happy when it gains 3 electrons. It just has to form a compound with something else in order to get those 3 electrons here. Again, polyatomic ions look more complex than they probably truly are. They still follow our rules. It's just they're covalently bonded molecules with a charge in order to become happy. Again, it's very, very, very important that we get the names and their formulas down. So go ahead and pause the video now if you haven't made this list yet, and make sure you are reviewing these on your own because these are not going away. So VSEPR theory is where all of this culminates to this idea that when I get a bunch of atoms forming compounds together, they're going to have a different amount of shared electrons. But not only that, because the electrons are all the same charge, electrons are negative, and negative charges or like charges are going to repel each other. These are going to create a shape that we can start to predict every single time. Or because they don't want to be next to each other, they're going to spread out as much as they can in order to make these 3-dimensional shapes, such as this. Well, I guess I'll draw that on the center atom there. Like this, where they're all going to be separated as far apart as they possibly can. Well, what VSEPR theory is, or what VSEPR stands for, or I always say it incorrectly, what VSEPR stands for is valence, shell, electron repulsion theory. Or it's this idea that all these negative charges are going to repel themselves because they're all electrons, and all of those electrons are negative, so they don't want to be next to each other, so they're going to separate out. What this is based on how many electrons we have and where they're located. So we have two different types of electrons, or more importantly, two different types of electron pairs. The first pair is the kind that we've seen really often, where they're found between two different atoms. We call those shared pairs of electrons, where they're going to be shared in between. We might call those bonded pairs as well, or bonded atoms. Bonded atoms, where they're bonded between those electrons being shared. We also have this very important other kind where we have something called a lone pair, where it's two electrons that aren't bonded next to any, or with two different atoms, but they are still repelling all of the other electrons here. Again, a note, a lone pair is going to only be on the central atom, or the ones we're worried about are just going to be on the central atom over here. So we have this VSEPR theory determined by all of the electrons, and we have to get more specific with lone pairs or shared pairs. The valence shell electron repulsion theory. A great example of this is balloons. When you put two balloons next to each other, they're going to naturally start to repel each other just because their shapes of the balloons are only going to force a certain shape. And the more balloons we add, the different shapes we're going to get, which will be note card number 15 here. Okay, VSEPR theory is going to give us a three-dimensional shape of every single molecule, but now what's important for us is to be able to determine which type of shape we're going to be given based on the number of lone pairs and bonded pairs. So that is going to be based on, again, when we get the Lewis structure for something, we'll go ahead and do that ammonia again, NH3. We have to look at how many lone pairs and how many bonded atoms we have on that central atom, and that's going to determine for us what is the shape of the molecule, what's its picture, three-dimensional shape going to look like, and then what is its bond angle here. So let's go ahead and do ammonia one final time, and we'll do one more after this. But ammonia is going to have a Lewis structure that looks like this. If you're not sure how to do this, go ahead and go back to, I believe, note card 8 or 9 or 10. You get a little refresher, but it has three atoms connected to this nitrogen. Now what we have to count is how many lone pairs are on the central atom and how many bonded atoms are on the central atom. Well, lone pairs are just on the top here, two electrons that aren't in between two separate atoms or elements. So we call that one lone pair. So we're going to look through this chart and find every option that has just one lone pair. Now I need to look for how many of them have 1, 2, 3 atoms bonded to the central atom. So I'm going to look in this next column for 3, and that'll be right here. So what we do is we go ahead and we look across this table, and we now know its shape, or we call this one, if you can't see it through the picture very well, trigonal pyramidal. And it's going to look like this. Well, the nitrogen's going to replace this E. It has its two lone pairs at the top, but we start seeing that there's an angle here where all of these are drawn at, or we're going to get like a wedge, or we get a dashed line. This is saying that these are on a two-dimensional plane right now, but they need to be represented in 3 dimensions. So it needs to look like this. Nitrogen is on top, and it has 3 separate legs. One where the nitrogen's here, then we have a hydrogen, and a hydrogen. The dashed lines and the wedges represent this hydrogen moving out of the paper towards you, and then the dashed lines are it's going into the paper back away from you. So we have to count how many lone pairs and how many bonded atoms there are to figure out what shape is going to be. I'm going to go ahead and do one more over here so we can start to get a kind of a better understanding of this. We're going to go ahead and do water, very simply water. Oxygen's in the center, 2 hydrogens on the outside, and we get 2 atoms connected to that oxygen. Well, everyone's happy now. We count how many lone pairs we have. 1, 2 on the central atom, and we count how many bonded atoms are on that oxygen, also 2. So we go back and we look, and we find, where do I find 2 and 2? Well, 2 lone pairs, 2 bonded pairs. We call that bent. It has a bond angle of 104 degrees, or that says it's 104 degrees between the 2 atoms together, and we're going to go ahead and draw it. So this water is going to have the shape that we call bent, and it's going to be drawn, again, bent, or at an angle. We'll still include all the lone pairs in the drawing, but it's going to look more simply like this. The VSEPR theory is the 3-dimensional shape. The molecular geometry name could be trigonal planar, could be tetrahedral, could be planar, or pyramidal, or it could be linear. And then the Lewis structure is what gives us all of the information that gives us what we need to find the VSEPR theory or the geometric shape.